Physics 211, Lab 1, Constant Velocity by Swayam Sanket Kumar Trivedi. Introduction. What is the purpose of this experiment? The objective of this experiment is to demonstrate Newton's first and second laws of motion through a real-world application of rolling a small, heavy ball across a table. This lab report will analyze the motion of the ball traveling at constant velocity in a uniform direction using tracker software and compare the observed trajectories using the graphs with predictions from a computational model developed in GlowScript. The fundamental physical principles used in this lab. The first one is Newton's first law, which states that an object will remain at rest or move in a straight line at a constant speed unless acted upon by an external force. What does this mean? If an object is stationary, it remains stationary, and if moving, it continues to move at that constant speed. Newton's second law states that if a force is acted on an object, then it starts to change, accelerate or decelerate. In short, it states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. If an object whose velocity is towards the right but is stopped by a wall, then it would cause a force that would be exerted on the wall into the ball, causing it to slow down and decelerate. Hence, a force is applied. Through this experiment, a force is applied in the other direction, causing the acceleration to change and slow down. Through this experiment, we see that the expected position versus time graph has a constant gradient, constant velocity, while the observed position versus time graph is a curve with a decreasing gradient with time decreasing acceleration. Formulas. What are the main formulas we will use throughout this experiment? The first one is the position update formula, which is RF, which is equals to RI plus the average velocity times the change in time. And the velocity update formula is the final velocity, which is equals to the initial velocity plus the net force over the mass times change in time. System surroundings. What is the system in the case of this? It is the ball from the foosball table that is rolling. And what is acting on this ball as it rolls across the table? There's drag, which is the air resistance that acts against it. There's the friction from the table as the surface is not smooth. There's gravity, which acts downwards, and the normal force, which acts upwards as a counter opposite of the gravity. Tracker data. I then uploaded this exact video onto the Tracker app, which then I was able to frame piece by piece the exact amount the ball traveled across the table. And I was able to calculate the average velocity of 0.726 using change in position over time. What was the initial position of the ball when it left my friend's hand? It was 0.00 meters. The initial time, on the other hand, was 0 seconds. I was then able to get the position time versus time graph as shown on the right-hand side of the slide. Through the values on the Tracker app, I was able to calculate the average velocity, which I plugged into my calculator and found the average velocity the ball travels at. I was then able to put this average velocity into GlowScript while maintaining the net force at 0, 0, 0. Through this, I was able to obtain the graph as shown on the right-hand side, and I used the position and velocity update formula to calculate my answers that I had shown on the previous slide. What does this tell us? When I compare the data of what I received on the GlowScript of what the expected value should be, while that on the Tracker app, which was what the value was as I received, I realized that the Tracker app gave data that was below what was the expected. Why was this? Well, it's simple. In nature, forces act on the ball. The surface is not smooth. As a result, the ball would start to slow down. We also have air resistance acting on the ball, which causes it in the opposite direction of the ball's motion, causing it to slow down. And assumptions. The assumptions I made were no friction force. There was no friction force between the table and the ball. There was zero net force. Only displacement is in the x-axis and not the y and z-axis. The surface is smooth. There's no drag, and air resistance is not acting on the ball. The errors. There's of course accidental human errors and accidentally changing the direction. What if, when you analyze your video data in Tracker, you made a choice of the orientation of the axis? Discuss briefly how your results would change or how they would remain the same if you were to flip the axis. If the axis were flipped and x was in fact negative, then everything would remain the same except the fact that the values would be negative. Hence the gradient would be negative, the magnitude would be the same, and the rate of change does not change. Can we say net force is 0? Your oscillations can be predicted well by your computational model when you set the net force equal to 0 in your model. Is it possible to say how many pushes and pulls, i.e. how many forces added together to give 0 net force in the case that you observed? Computational models are able to calculate with Fnet because being 0. However, in real life, this is not the case. The gravity that pulls everything to the center of the earth and friction in moving objects cause nothing to have a net force of 0.